So you've looked at electrodynamics and you're ready to get into circuits. But we need to transition there, and the best transition chapter for that is chapter 26, concerning capacitors. A capacitor is a device used in electric circuits for, one thing is charge storage. If you look at a motor, a lot of times you'll see a large capacitor right in the vicinity of the motor, and what that's trying to do is store charge so you can get an extra surge when you need to start that motor, and that allows you to overcome stack friction. Frequency tuning in the AC circuit. Capacitor in conjunction with an inductor will allow you to resonate an AC circuit, and with that resonant frequency you can pick up the same kind of frequency in the airwaves, use it as a receiving device, amplify that signal so that you can tune to that signal. Voltage control. Many times if you look at a circuit diagram, you'll see a capacitor right at the entrance to your circuit. And what it's trying to do is to hold the voltage near a specific value so it doesn't fluctuate too much with your incoming signal. Also, it will serve as a filter to filter out noise coming into your circuit. These are all great things that capacitors can do. We define the capacitance of a device as a measure of its ability to store charge given a potential difference. So we say capacitance is equal to the charge divided by the voltage, or the charge divided by the potential difference. Excuse me. A capacitor will consist of two conductors separated by an insulator, or a dielectric is what we call that. If you take this formula for the definition of capacitance and just rearrange it, you have the charge is equal to the capacitance times the voltage. We will use this second form of this formula so much that you want to take note of it. Q is equal to C times V. The unit of capacitance is the farad. That's equal to a coulomb per volt, named after Michael Faraday. Most capacitances that we are going to look at will be in the range of microfarads to picofarads. If you have 1 farad capacitance, that's a really large capacitor. That's probably what you would see near a motor, or maybe a half a farad. You know, something that can hold a lot of charge. But if we're working in circuits, we don't need that much. So we're going to be dealing with microfarads, nanofarads, picofarads, possibly millifarads. Here's what it might appear. Say if you had something like this, that might be like 1 farad capacitance. Or if you had something like this, that could be a microfarad. If you have a 2 microfarad capacitance, it'd be something like that. Or if you had a smaller value, you could have a picofarad. Definitely an example where your instructor has too much time on his hands. A spherical conductor capacitor consists of a spherical conducting shell, radius B, concentric with a smaller conducting sphere, a radius A, and charge Q. Find its capacitance. So we have 2 nested shells, plus Q on the inside, negative Q on the outside. We want to find the capacitance of this device. Well, note that if you're inside the outer shell, that there will be no electric field due to that charge, because you could build a Gaussian surface as close to that inner surface as you could and never enclose any of that shell's charge. Hence, the E field there would only be due to the shell inside. So for the space between these 2 conductors, from radius A to radius B, the E field is only due to that inner shell of charge Q, plus Q. And that since we're outside of that shell, it's acting basically like a point charge at the center. So it's acting like an E field of a point charge equal to KQ over R squared. From last chapter, we have that the potential difference between 2 conductors is equal to a negative integral from point A to point B, E field, dr, if we're going in a radial direction. In this case, that E field is indeed kq over r squared due to the inner sphere. So we have that the potential difference is negative kq, integration from radius A to B, dr over r squared. So that's a pretty easy integral. That's just 1 over r, evaluated here from A to B. And so we're going to have kq, 1 over b, minus 1 over a. Find a common denominator for those two fractions. So we'll multiply them each by 1. And we have that this potential difference is kq, a minus b over a times b. Bear with me, we're doing this for a reason. So the magnitude of that potential difference will be kq, b minus a over a times b, because b is greater than a. And hence our capacitance of this device will be the charge divided by the magnitude of the voltage, and that's the charge will cancel out, and we'll have that the capacitance is a times b over our famous K electric constant, 9 times 10 to the 9, b minus a. What's cool about this result is that it only depends on geometric factors. It only depends on the radius a, the radius b, and a constant, our famous K constant, 1 over 4 pi epsilon naught, or 9 times 10 to the 9. So you could build these capacitors based on those specifications in the factory without having to know what charge you're going to try to put on it or the voltage you're trying to put on it. It's basically based on geometric factors. What's the capacitance of an isolated spherical conductor? Well, to isolate a spherical conductor, let's just take our result that we just got for nested spheres, and we'll take the outer sphere and move it all the way to infinity. If we do that, B will approach infinity and will basically isolate the sphere that's left, the sphere of radius A. So let's do that. Let's take our result from the nested spheres, and we're going to make B approach infinity. Now when B approaches infinity in this fraction, we're going to have A times infinity over K times infinity. And believe it or not, infinity divided by infinity is actually 1. So we're going to have that the capacitance will approach the value of radius A divided by K. How about that? The capacitance of an isolated sphere of radius A is the radius divided by our famous K constant, 9 times 10 to the 9. Since K is 1 over 4 pi epsilon naught, we could also express this as 4 pi epsilon naught times the radius A. That is one little result that I wish you to remember. So, based on this, what is the capacitance of the Earth? Treating the Earth as a sphere, radius 6.37 times 10 to the 6 meters, the capacitance is the radius of the Earth, 6.37 times 10 to the 6, over our famous K constant, 9 times 10 to the 9, 7.08 times 10 to the minus 4 farads. Not very much, but that's the capacitance of a sphere the size of the Earth. We're also interested in a parallel plate capacitor. If we recall from chapters 23 and 24, if you had an infinitely charged sheet, the E field near that is equal to the surface charge density sigma, charge per area, over 2 epsilon naught. And it's constant near that infinitely charged sheet. If I had one positively charged and brought in a negative charged one as well, those two E fields would actually be in the same direction, because the positive one is emanating outward and the negative one has one going into it. So the two E fields will add, and hence we'll have a constant E field between those two plates equal to sigma over epsilon naught. Sigma is the surface charge density. It's the charge per area on either one of those plates. So since we have a constant E field, our voltage will be constant as well, and will be equal to the E field times d, d being the distance between the plates. So that's going to be equal to sigma over epsilon naught times d, where d is the separation distance between those parallel plates. Now, using our definition of capacitance, we know capacitance is the charge divided by the voltage. In this case, the charge is our surface charge density, sigma, the charge per area, times the area. That will give us the total charge on one of those plates, divided by the voltage that we just calculated, sigma over epsilon naught times d. Our sigmas cancel out here, and we get that the E field between these parallel plates in air or a vacuum is equal to epsilon naught, the permittivity of free space, times the area of one plate over the separation distance d between the plates. So this is the parallel plate capacitance, where A is the area of one plate, D is the separation distance, and epsilon naught is the permittivity of free space, that famous universal constant that you know and love, 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. What's neat about this result is, again, it only depends on geometric factors. How big are the plate, A, and what is the separation distance between the plates, D. If we put an insulator in between these plates, we can actually increase the capacitance. Now, the capacitance of an air-filled capacitor is what we just found, epsilon naught A divided by D. But if we put an insulator, which we call a dielectric, put that in between, we basically replace the permittivity of free space, or of air, with the permittivity of the material that we put in between. So we're going to replace epsilon naught with epsilon. And our new capacitance will be epsilon, for whatever that material is, times the area over the separation distance d. Well, epsilon is the permittivity of that material, but we express it as being a constant times the permittivity of free space. So we describe epsilon as some constant kappa times epsilon naught. And that kappa is what we call the dielectric constant. It is a constant intrinsic to that material, and it is a constant that dominates 1. So always be greater than 1 or equal to 1 if it happens to be a vacuum. But it will never be less than 1. So here are some dielectric constants. For a vacuum, it's 1.00000000. For air, it's 1.00059, so basically it's 1. For paper, it's 3.7. So if I took paper and stuffed that in between the two parallel plates, I would increase its capacitance by a factor of 3.7. In other words, it would have more capacitance to hold charge given a certain voltage before it would discharge. So the insulator allows it to insulate itself from a discharge between the plates. Surprisingly, if I put water in there, it has a dielectric constant of 80. We would have more other problems with water being a polar molecule, but at least as far as the capacitance goes, its dielectric constant is 80. For strontium titanate, the dielectric constant is 233. So I can make a very good capacitor, increase its capacitance by a factor of 233 with strontium titanate. Let's try this out. A parallel plate capacitor has plates of dimensions 2 centimeters by 3 centimeters, separated by a 1 millimeter thickness of paper. The dielectric constant for a paper is 3.7. Find the capacitance of this device. We'll have C is equal to kappa, the dielectric constant, epsilon naught, the permittivity of free space, area over the separation distance. That's 3.7 times 8.85 times 10 minus 12. 6 times 10 to the minus 4 for the area, because 2 centimeters by 3 centimeters is going to be 6 square meters, or 6 times 10 to the minus 4 square meters over 1 millimeter. That gives us a capacitance of 20 picofarads. 20 times 10 to the minus 12 farads. So that is 20 picofarads. That concludes the first part of chapter 26, which is just to use where we've just been to kind of segue ourselves into circuits. Our main two results of this first part is our two values for the capacitance. First, of an isolated sphere, radius over K, and then of a parallel plate capacitor, kappa epsilon naught A divided by D. So those are the two results you need to remember from this first lecture in chapter 26.